I don't really like to use a lot of class time to go over homework, so I just wanted to review a couple of the homework problems. You can always check out the solutions online on Moodle, but I worry sometimes that you don't. So I want to make sure that you are aware of a couple of places that a lot of you are going wrong. For instance, in the Halliday, Resnick, and Walker problem number 29 on the most recent homework that you had in that text, it gave you a function which looked something like this. I can't remember. Some constant times some omega. So, whoops, it wasn't an omega. So the function looked like this. And what's really important for you to realize is that there is no reason to think, by looking at this function, that it's an equation of a wave. It's not. We showed that the solutions to the wave equation were, for example, sines and cosines. But this is not a sine or a cosine. So this is not an equation. This is not something that we know of as an equation of a wave. So most of you just assumed that this was just like a sine and a cosine, but there's no reason to assume that. The only way we can know that this is an equation of a wave is to plug it into the wave equation. D squared y dt squared equals d squared y, or psi, doesn't matter which function we use, dx squared, and then c squared or v squared here. So the only way we know it's a wave by plugging it into that, and the only way we can find the velocity is to solve for v when we plug the function, the new function, into the wave equation. And the book problem explicitly said, use the wave equation to determine the velocity. So you can't just assume that the velocity is going to be a over b or b over a, because it's not something that we know of as a wave. The only things that we determined were waves were functions that look like a sine kx minus omega t plus phi. That's the only thing that we determined were waves. Anything else we're going to have to prove is a wave. We had to prove that what's in the box was a wave, and anything else we would have to prove is a wave. So most of you did attack 29 in the incorrect way. And you can certainly expect to see something like that on an exam. Then, in the next homework, on number 25 from our text, from the modern physics text, most of you, let's just put a 29 here. Most of you just assumed that the function looked like a sine kx minus omega t, which was incorrect. You didn't pay attention to the phase, right? There is a phase there. When we're talking about what happens in time, we may not care about the phase, but it was asking for the function, and it gave you initial conditions, and the phase is determined by the initial conditions. And the initial condition was that the function is a maximum at t equals 0. And this equation is not a maximum at t equals 0, right? The general equation is a sine kx minus omega t plus phi, and sine or cosine, it doesn't matter. And in order to make that a maximum, either, right, to make that so if the function psi equals, if the function is a maximum, psi is equal to a at x equals 0 and t equals 0, then phi has to be, if phi was 0, then psi would equal 0. So phi has to be pi over 2 or minus pi over 2 or something like that. So you got the phase wrong in that problem, most of you. The other way to do it is to say, oh, well, what's maximum at t equals 0 and x equals 0 is a cosine. So this is the same as a cosine function. So a cosine kx minus omega t would also work. But you just made an assumption of the incorrect form because you didn't pay attention to phase, and so that was what led you to a wrong answer. And then in addition, this was a problem where you need to pay attention to what amplitude means in context. It asked what the amplitude, so the next part was, the last part of the problem was, it asks what is the amplitude at a certain x and t. So when it's asking what is the amplitude at a certain x and t, it's not asking what is the maximum value. Oops, I didn't mean to scribble that out. It's not asking what is this value. It's asking what is this value? What is the amplitude? What is the size of the wave function at a certain x and t. So you've got to take the context. If it asks what is the amplitude at a certain x and t, it means what is the size of the wave function at x and t. A few of you just gave me a, which it turns out I believe the answer was the amplitude was maximum at that point, but it was unclear that you understood what it was asking for. So you need to take that when a problem asks for amplitude, you need to take the context to know whether it's asking for the value of the wave function or whether it's asking for the maximum value of the wave function. The last general issue that was unclear to me that whether you understood or not was problem number 27 from our text. Problem number 27 from our text asked for the spacing between two zeros, I believe. And just make sure you understand that what is a zero? This is a zero, this is a zero, this is a zero, and this is a zero. So the spacing between two zeros, if this axis is x, is equal to half a wavelength, and not a full wavelength. A few of you made it a full wavelength. So there are multiple zeros in a full wavelength. So just to make sure you understand what it means to talk about the spacing between two zeros. And that's what we mean by the width of a wave packet. That's all I got.